Hello everyone, this is Introduction to Robotics Lecture 2, Part 1. We will talk about space transformations. What is a robotic manipulation? Robotic manipulation, by definition, implies that parts and tools will be moved around in space by some sort of mechanism. This creates a need for representing positions and orientations of parts, of tools, and of mechanism itself. To define and manipulate mathematical quantities that represent position and orientation, we must define coordinate systems and develop conventions for representation. The most known is the universe coordinate system. Now we will talk about positions, orientations, and frames. A description is used to specify attributes of various objects with which a manipulation system deals. These objects are parts, tools, and the manipulator itself. We will discuss about the description of positions, of orientations, and of any entirety that contains both of these descriptions, the frame. What is a position? Once a coordinate system is established, we can locate any point in the universe with a 3x1 position vector. The position vector AP means that the components of the AP have numerical values that indicate distances along the axis of A. Each of these distances along an axis can be thought of as the result of projecting the vector onto the corresponding axis. You can see this representation in figure 2.1. Individual elements of a vector are given the subscripts x, y, and z. So for the vector AP we have the elements px, py, and pz. Next we have the orientation of the vector. We can see here a robotic manipulator that is trying to locate an object in position and orientation. The hand locates the point directly between the fingertips of a manipulator hand. The complete location of the hand is still not specified until its orientation is also given. To describe the orientation of the body, we will attach a coordinate system to the body and then give a description of this coordinate system relative to the reference system. Assuming that the manipulator has a sufficient number of joints, the hand could be oriented arbitrarily while keeping the point between the fingertips at the same position in space. In figure 2.2, the coordinate system B has been attached to the body in a known way. A description of B relative to A now suffices to give the orientation of the body. One way to describe the body attached coordinate system B is to write the unit vectors of its three principal axes in terms of the coordinate system A. The unit vectors giving the principal directions of coordinate system B, xb, yb, and zb. In terms of coordinate system A, they are xb in reference to A, yb in reference to A, and zb in reference to A. The rotation matrix that describes B relative to A is R from B to A, and you can see here this representation. The rows of the matrix are the unit vectors of A expressed in B. So we can write that the rotation matrix from B to A, it is the rows of the unit vectors of B expressed in A, that it is equal with the transpose unit vectors of A expressed in B. Note here that the position of a point is represented with a vector. The orientation of a body is represented with a matrix. Now let's see the frames. The description of a frame A relative to B can be given as the rotation matrix from B to A, that it is equal with the transpose rotation matrix from B to A. The inverse of a rotation matrix is equal to its transpose, a fact that can be easily verified as the multiplication of these two matrices, and we can see that they have a product, that it is the identity matrix. The frame, it is a set of 4 vectors giving position and orientation information. The description of a frame can be thought of as a position vector and a rotation matrix. Note that the frame is a coordinate system where, in addition to the orientation, we give a position vector which locates its origin relative to some other embedding frame. A frame is depicted by 3 arrows representing unit vectors defining the principal axis of the frame. An arrow representing a vector is drawn from one origin to another. This vector represents the position of the origin at the head of the arrow in terms of the frame at the tail of the arrow. The direction of this locating arrow tells us, for example in figure 2.3, that C is known relative to A and not vice versa. Now let's talk about translational operators. The operation of translation moves a point in space a finite distance along a given vector direction. With the interpretation of actually translating the point in space, only one coordinate system needs to be involved. It turns out that translating the point in space is accomplished with the same mathematics as mapping the point to a second frame. In figure 2.9, we can see how a vector A P1 is translated by a vector AQ. Here, the vector AQ gives the information needed to perform the translation. The result of the operation is a new vector AP2 calculated as AP2 is equal with vector AP1 plus AQ. We can also write this operation as a matrix operator where AP2 is equal to DQ matrix of Q times AP1. The rotational operators just explain how we can rotate a vector. This operation is written as a vector AP2 is rotated and it is equal with the rotation matrix R times vector AP1. The rotation matrix that rotates vectors through some rotation R is the same as the rotation matrix that describes a frame rotated by R relative to the reference frame. The operator clearly indicates which axis is being rotated about. We can also describe the operation of rotation as a new vector AP2 that is equal to the matrix RK of theta times AP1. In the notation, RK of theta is a rotational operator that performs a rotation about the axis direction k by theta degrees. Next we have the transformation operators. The operator T rotates and translates a vector AP1 to compute a new vector. AP2 is equal to T times AP1. The transform that rotates by R and translates by Q is the same as the transform that describes a frame rotated by R and translated by Q relative to the reference frame. So we can say that the matrix operator T combines both translation and rotation. This was the first intuition about space transformations. In part B, we will talk more about angles, Euler angles and homogeneous transformations. Thank you very much.